Section 12.1, Section 12, Chapter 12 is all about circles, and Section 12.1 is entitled Tangent Lines. And it just so happens to be Pull Me in Your Pocket Day, apparently. I learned that that's actually a thing. So, anyway, um, we're going to do lots of things related to circles in this chapter. Our goal for Section 12.1 is up here, to use properties of a tangent to a circle. So we've learned about tangents when we're dealing with trigonometry. Now we're going to learn about tangents to a circle. So let's start off. A tangent to a circle is a line in the plane of a circle that intersects the circle at exactly one point. It intersects the circle at exactly one point. And that point would be right there, B. So it's a line that it essentially just scrapes the circle. It touches it at exactly one point. And it's hard to tell if it touches exactly one point, but if it looks like it does, we're going to assume that it does, and that would be a tangent line. A tangent line just touches the circle at exactly one point. And that point where a circle and a tangent line intersect, so that point B is called the point of tangency. Point of tangency. All right. So it's important to know right here, radius of a circle and the tangent line that intersects the endpoints of the radius have a special relationship. So if it's a tangent line and the point where that tangent line and the radius intersect have a special, those two lines have a special relationship, and that's coming in our first theorem here, Theorem 12.1. It says, if a line is tangent to a circle, then the line is perpendicular to the radius at that point of tangency. So in our example, if segment AB is a tangent to circles O at the point P, then segment OP is perpendicular to line AB. All right. So let's use that now. That remember that makes 90-degree angles. So example 1 and 2 here. Lines that appear to be tangent are tangent. Let's just assume that. O is the center of each circle, and we want to find the value of x. So if we look at this, how we can apply that theorem is right here. We have a point of tangency. It touches it only at one point. This line right here is not a point of tangency because it crosses the circle at 2 points. If it only touches at one point, it is a point of tangency, which makes a right angle because it's perpendicular to that radius. And so if that's 90 degrees and this is 36 degrees, then x would have to be equal to whatever, well, essentially 90 minus 36, because total it's 180 and this is already 90. So I'll use 90 for these other two angles, and that would be equal to 64 degrees. X is equal to 64 degrees on that one, or 64 if it already has the degree sign with it. Number 2 is a little bit more tricky. All we're given is this one angle of 53 degrees. Now we know because there's a point of tangency right here that this total would be a right angle, meaning that that other part next to it would be a, or sorry, 53 degrees. That would be a 27-degree angle. Sorry, 37-degree angle. But we really want to find the angle of x. So we're going to have to look at a triangle. We'll either have to find this, looking at this whole big triangle, or look at this smaller section. So let's just look at what we've got. This took me a while to think about too. But remember, all radii are congruent. So if these two are congruent, that forms a isosceles triangle, meaning the isosceles angles, the ones opposite of the congruent sides, are going to be congruent. So that means that this angle right here is also 53 degrees, which leaves, well, that means the opposite side, if this is a line, would have to be whatever 180 minus 53 is. 180 minus 53. What's it going to be? 127? Let's borrow from here. Yep, 127. That's a 127-degree angle. And if we look at the smaller triangle, so I'm gonna highlight the triangle that I'm dealing with here just to help you out. This, this, this. We've got one angle is x, one angle now is 127, and this third angle would be 90 minus 53 because of our tangent line here. So that would be 37 degrees. And if we take that and add them all up to 180, we'd do 180 minus, well, what's 37 plus 127? That would make 164, so minus 164. And I'll borrow here. 7, 1, 6. 7 minus 6 is 1, so 16 degrees. 16 degrees for that angle right there, a very small angle. All right, hopefully I did that math in my head correctly. Now here's one that I like to do in class with you, but I'd also like you to try on your own. Number 3 gives you some information. It gives you a whole lot of lines, a couple tangent lines, some radii, and some diameters. Try to find these two angles. All right? May have to find one before the other, but they're both doable. But right now we're going to go on to the converse of that. Theorem 12-2 is the converse of it, and it can be used to prove that a line or segment is tangent to a circle. Remember, the converse is just flipping the order. So before we said if we have a tangent to a circle, then that line and the radii that touches that tangent point would be perpendicular. Now it says in this theorem, if a line in the plane of a circle is perpendicular to a radius at its endpoint on the circle, then the line is tangent to the circle. So then we know that AB, line AB is a tangent line. And it only crosses at that one point. Alright, so we got two examples here to do that. How can we tell if they are tangent or not? Well, we got to figure out if they're perpendicular or not. So how do we figure out if they're perpendicular or not? Using a little trigonometry. So right here, we have three sides of a triangle. It says determine whether a tangent is shown in the diagram. Well, to see if it's tangent or not, let's use the Pythagorean theorem. That right triangles go with the Pythagorean theorem, so it'd have to be 7 squared plus 15 squared would have to be equal to 16 squared. 7 squared we know is 49. 15 squared I believe is 225. And 16 squared, I don't have off the top of my head. I think it's like 256-ish. I'll do it on here. 256. Nice. Good guess. All right, 225 plus 49 will get you oh, sorry. Would get you 270 something? 274. Those are not equal, so it's not a right triangle, meaning that it is not a tangent line. So at some point, maybe this will go through another point. I'm not sure how this will work, but it is not a tangent line to that circle. All right, next example, find the value of x to the nearest tenth. We're assuming it's a rectangle, or a right angle. So we're assuming it's a tangent line, meaning we're assuming that, well, if we're dealing with triangles again, might as well use the Pythagorean theorem. We can do x squared. We're trying to find x, so x squared plus 8 squared equals, 5 plus x squared, or x plus 5 squared. Ooh, that's annoying. I think we're going to deal with a quadratic here eventually. So I'm going to have you try to finish this one on your own. I'm going to pause it right now. All right, so I factored here, or I didn't factor, I distributed. I did x plus 5 times x plus 5, and I got x squared plus 10x plus 25. And that would be equal to x squared plus 64. So we didn't have to deal with the quadratic because we could, the x squared canceled out on both sides when you subtracted an x squared. And then I got it to the point where 10x is equal to 39, and I got x equals 3.9. Now, I'm not going to go back and check it. If you'd like to check my work and see if there's an error in there, go for it. But I'm going to move on from here. That's how we were just using that converse. Oh, there's a poem in my pocket. I just found a poem in my pocket. So I'm going to read it to you. This is a poem that I actually wrote about my dying car a few years back. Tinkle, tinkle, little car, how I wonder what you are. Leaking oil every day, having it your own way. Rusting away really slow. I don't want you anymore. Tinkle, tinkle, little car, boy, what a piece of junk you are. And that was about my car, Big Red. I called it Big Red because it was actually a really little car that was red. And it turned out to be a piece of junk. But it was my first car. So anyway, moving on from there, that was the poem in my pocket on Poem in My Pocket Day. We have one more theorem. This is Theorem 12.3. It says if two tangent lines to a circle share a common endpoint, like the picture drawn right here. Two tangent lines sharing point B. Outside of the circle, then the two segments are congruent. Okay, if they're truly tangent lines and they'll truly cross at one point, then this is congruent to this. So AB, segment AB, is congruent to segment BC. Okay, so in the figure to the right, the sides of the triangle are tangent to the circle. The circle is inscribed in the triangle. Whoops. Oh man, what's happened? The triangle is circumscribed about the circle. Some words just so you can remember back when we learned these originally. So now I have one example here to work with this theorem. It says circle B is inscribed in the triangle, which has a perimeter of 76 inches. So total, that's 76. What is the value of x? Ooh. All right. Well, let's look at that theorem. We know from that theorem that assuming these are tangent lines, we're assuming that they are. And this has to be equal to this. This has to be equal to this. And this has to be equal, I should probably use double, has to be equal to that. So this part right here has to be 25. This part right here has to be x. And this part right here has to be 5. And the whole total perimeter is 76 inches, so let's just use that. So 76 equals 5 plus 5 plus 25 plus 25 plus x plus x. Okay, so 76 equals, and you can do the math from here, 25 plus 25 is 50, plus 5 plus 5 would give me 60, equal, and then x plus x, sorry, I should do a plus here, 2x, subtract 60 from both sides, we get 16 equals 2x. That would mean that x is equal to 8. And that's really a basic way to utilize this theorem. So that's the last example we're going to do. Take a look at the two. This actually homework won't necessarily apply to you. So we're going to toss it off to the side. But closing questions. Please answer the closing questions. What type of angle is formed at the intersection of a tangent and a radius of a circle? And what is the relationship between two segments drawn from the same point tangent to a circle? And that is it for section 12.1 on tangents of a circle.